orthogonality. So what is direct sum? A vector space X is said to be direct sum of two subspaces Y and Z of X if each X belonging to X has a unique representation like X equal to Y plus Z. Here Y belongs to Y and Z belongs to Z, and we write X equal to Y, direct sum of Y and Z like this. This is called O plus, and Z is called the algebraic complement of Y in X, and Y is called the algebraic complement of Z in X, and together we called YZ to be complementary pair of subspaces in X, and this Y is called the orthogonal projection of X on Y. So what is orthogonal complement? An orthogonal complement, which we denote like this, of a subset S of H is a set of all X belonging to H which are orthogonal to all elements of S. It means we say that X belongs to orthogonal complement of S if and only if inner product of X with Y is equal to 0 for all Y belonging to S. So from here we see that if Y is equal to R is a subspace of Euclidean plane R square, then Y has infinitely many algebraic complements in R square, each of which is a real line. But most convenient is a complement that is perpendicular. We make use of this fact when we choose Cartesian coordinate system, and in R cube means 3-dimensional space, the situation is the same in principle. Similarly, in the case of general Hilbert space H, the main interest concerns representation of H as a direct sum of closed subspace Y and its orthogonal complement, which is a set of all the vectors orthogonal to Y. So first of all, we will show that this orthogonal complement of S of a Hilbert space H is a closed subspace of H. To show that orthogonal complement of S is a closed subspace, first of all we will show that this is a subspace, then we will show that it is closed. So to prove that that is a subspace, we will show that it is closed under the addition and scalar multiplication. Suppose U and V belongs to orthogonal complement of S. So by definition, inner product of U with W equal to 0 and inner product of V with W equal to 0 for all the points W of the set S. This is by definition of orthogonal complement of S. Now what is inner product of U plus V with W? Inner product of U plus V with W is inner product of U with W plus inner product of V with W. But this is 0, this is 0. It means inner product of U plus V with W is also 0, and it means U plus V belongs to orthogonal complement of S. Also, inner product of CU with W is equal to C times inner product of U with W. And this is given to be 0. It means C into 0 is 0. It means inner product of CU with W equal to 0 for all W belonging to S and C belonging to F. C is a scalar, it belongs to field. It means CU belongs to orthogonal complement of S complement. So we have shown that orthogonal complement of S is closed under addition as well as scalar multiplication. Also, inner product of 0 and S belongs to 0 for any S belonging to S. It means 0 belongs to orthogonal complement of S. It means S complement, orthogonal complement of S is a subspace of H. Now we will show that it is closed also. Let X be any element in the closure of orthogonal complement of S. Hence there is a sequence Xn in orthogonal complement of S such that Xn tends to X. Now for any Y belonging to orthogonal complement of S, we have inner product of X with Y equal to inner product of limit xn as n tends to infinity with y, and we can write it as limit n tend to infinity. We can write outside also inner product of xn with y, but xn is a sequence in orthogonal complement of S. It means inner product of xn with y is 0. So it means inner product of x with y equal to 0. Hence x belongs to orthogonal complement of S. Means this contain all its limit point. It means orthogonal complement of S is closed. So we have proved that orthogonal complement of any non-empty subset of a Hilbert space H is closed subspace of H. Now the orthogonal complement of a closed subspace of a Hilbert space is a null space NP of the orthogonal projection P of H onto Y, and it is a special annihilator. The annihilator orthogonal complement of M of a set M is an inner product of product space X is the set orthogonal complement of M equal to X belonging to X such that X is perpendicular to M. It means X belongs to orthogonal complement of M if and only if inner product of X with V equal to 0 for all V belonging to M. This explains the name. Note that orthogonal complement of M is a vector space. We have shown in last slide also, but here in short we say that because xy belongs to orthogonal complement of M implies that for all V belonging to M and all scalars we have inner product of ax plus beta y with V equal to a times inner product of x with V plus beta times inner product of y with V. It means this is 0. It is given to us. Also y inner product of I with V is also 0 because y belongs to x and V belongs to M. Hence inner product of alpha ax plus beta y with V is equal to 0. It means in ax plus beta y belongs to this orthogonal complement of M. And we write if we have orthogonal complement of M, then we write it like this. In general, M is a subset of orthogonal complement of M because X belongs to M implies X is orthogonal to orthogonal complement of M. It means X belongs to this. M is a closed linear subspace of Hilbert space H. Then we can write H equal to direct sum of M and its orthogonal complement. Because M is closed subspace of a complete space H, we know that H is complete because Hilbert space is a complete inner product space, so it is complete. So it means M is also complete. Let X belongs to H. Then we have studied in previous lecture that if M is a closed linear subspace of Hilbert space H, then we can write Z equal to X minus Y, and this Z is orthogonal to H. Or we can say that Z belongs to orthogonal complement of M. Hence, for every X belonging to H, there is a Y belonging to M such that X is equal to Y plus Z. We have shifted this to this side. So X equal to Y plus Z, and Z belongs to orthogonal complement of M. Now we have shown that we can express any element X of H like Y belongs to X as Y plus Z, where Y belongs to M and Z belongs to orthogonal complement of M. Now we will show that this representation is unique. Suppose this representation is not unique, and x is equal to y plus z, also x is equal to y1 plus z1. Here y and y1 are elements of M, and z and z1 are elements of its orthogonal complement. Because x is equal to y plus z and x is equal to y1 plus z1, it means y plus z is equal to y1 plus z1. If we shift y1 to this side and z to this side, then y minus y1 is equal to z1 minus z. Since y minus y1 belongs to M and z1 minus z belongs to orthogonal complement of M, but z1 minus z is y minus y1. So it means y minus y1 belongs to M, also y minus y1 belongs to orthogonal complement of M, because z minus z is same as y minus y1. So it means it belongs to their intersection. Means y minus y1 belongs to M intersection orthogonal complement of M. But this is equal to singleton set 0, since M is a subspace and hence contains the 0 vector. It means y minus y1 equal to 0, or we can say y equal to y1. It's if y minus y1 is 0, then z1 minus z is 0. It means z1 equal to z. So we have proved y equal to y1 and z1 equal to z. It means this representation is unique. Hence x belongs to H has a unique representation as x equal to y plus z, where y belongs to M and z belongs to orthogonal complement of M. So we can write H as a direct sum of M and its orthogonal complement. This is by the definition of direct sum. Here y is called the orthogonal projection of x on M, or briefly the projection of x on M. This term is motivated by the elementary geometry. For instance, if we take h equal to r square and project any x equal to xi1 xi2 on xi1 axis, which then plays the role of M, the projection is y equal to xi1 0. Equation x equal to y plus z, where z belongs to z, which is equal to orthogonal complement of y, defines a mapping P from h to y. It takes x to y, where y is equal to px, means image of x under P. This P is called the projection, and in fact it is the orthogonal projection, or it is also called projection operator of h onto y. Obviously P is bounded linear operator. This is y equal to px, this is z equal to pzx, and this is x. Here P maps h onto y onto itself, and z equal to orthogonal complement of y onto singleton set 0. And this is idempotent, means p square equal to p. Thus for every x belonging to h, p square x is equal to p of px, and this is equal to px. It means the restriction of p to y is identity operator on y. Now we will show that square root of inner product of x with x has properties of norm. We know that this expression is the square root of the inner product of x with x, and also we know that norm x is equal to square root of inner product of x with x. So first of all we will check that whether it satisfies all the properties of norm or not. So first of all, for any x belonging to h, the square root of inner product is always non-negative, because square root of non-negative number is non-negative itself. Secondly, square root of the inner product is equal to 0 if and only if vector x is the 0 vector, means inner product of x with x equal to 0 if and only if x equal to x. Thirdly, for any scalar alpha and vector x belonging to h, we have inner product of alpha x with alpha x equal to alpha bar inner product of x with x, because here alpha is on the left side, here alpha is on the right side. So this is the alpha on the left side, this is alpha on the right side, so it will come out as alpha bar. means conjugate of alpha, and alpha bar is mod alpha whole square. So if it will come outside of square root, it will be mod alpha. So square root of inner product of alpha x with alpha x is modulus of alpha times square root of inner product of x with x. So scalar multiplication is also satisfied. Now we will check the triangle inequality. So inner product of x plus y with x plus y is inner product of x with x plus inner product of x with y plus inner product of y with x plus inner product of y with y. And we have square root on all the terms. Here also we have square root of all the terms, so I have written round bracket here. So this is inner product of x with x, this is inner product of y with y. Now inner product of x with y plus inner product of y with x is equal to twice the real part of inner product of x with y. And this is less than or equal to inner product of x with x and inner product of y with y. By Cauchy-Schwarz inequality, real part of inner product of x with y is less than or equal to inner product of x with x and inner product of y with y, and this is this too. So for this I have used this inequality, and this is same, and this square root is on the whole term. So if you see clearly, this is a square, this is b square, and it is 2ab. In place of a, I have square root of under root square root of inner product of x with x. In place of b, we have square root of inner product of b with b, and this is square of this because here we don't have square root in this term, and here this is square of this because we don't have square root here, and this square root is on the whole term. So a square plus b square plus 2ab is a plus b whole square. So this is square root of x, inner product of x with x, plus square root of inner product of y with y, and this square root and this square will go. So we are left with inner product of x with x plus inner product of y with y, because a plus b whole square under root is a plus b. So inner product of x with x plus inner product of y with y. So we have shown that inner product of x plus y with x plus y is less than or equal to inner product of x with x plus y with square root of inner product of y with y. So we have shown that it also satisfies the triangle inequality. Thus the expression square root of inner product of x with x satisfies the four conditions necessary for function to be considered as a norm. We know that a function norm function satisfies the four conditions, that norm x is greater than or equal to 0. This is the first one. Norm x equal to 0 if and only if x equal to 0. This is the second one. And norm of alpha x equal to modulus of alpha times norm x. This is the third one. And norm x plus y is less than or equal to norm x plus norm y. This is similar as the fourth one. So this square root of inner product of x with x satisfies all the four conditions necessary for a function to be considered as norm. So we have proved the result. Thank you.